students, it's Mr. Bornheimer, and this is the Physics Unit 2 PowerPoint. Now, a couple things about this PowerPoint. First of all, this is just part 1. This is just like the introduction to Unit 2. And this is going to be more of an overview of what we already talked about in class. If you've missed out on any of these notes as we go along, I'll give you the words that you can go ahead and fill in the blanks. But otherwise, yeah, just be aware of the fact that as I work through this, if you have any questions, you should probably email me. So here we go. Okay, the big idea for this particular unit is that you can use, let's go back a little bit here. The big idea is that you can use velocity and displacement to go ahead and describe how an object moves. Now, you can use motion diagrams to show how an object's position changes over, and the blank for this here would be time. Okay, so when we're looking at describing an object's motion, we describe it, okay, first as where's it at, and how did it get there, how long did it take? Or where's the object at, where's it going, how long will it take? All right, so these are the questions that we have to ask ourselves. The essential questions that we're going to answer in this particular presentation are listed here. Okay? What goes in this blank here would be the word model. Okay? When we're talking about things in physics, we're talking about modeling motion. So in this particular case, it's like, okay, a model is a representation of an idea, event, structure, object. Think about for the moment if you have like a fashion model, okay, and they walk down a runway. Now that's fine, but what really are they representing? They're representing an idea, some designer's idea that he wrote down that then he designed and put it on a model so that people could see it and talk about it and engage in this idea. And when you ever if you ever see a designer that's questioned after some kind of fashion show, they'll ask him, what were your thoughts when designing these things? So yeah, a model is a representation. Posters are the same way, diagrams, okay? So when we're modeling motion, we're taking ideas and we're shaping them into something else, something that we can either understand or that we can share that is useful for everyone. Okay? Now, motion's all around us. Here's just some couple of examples. You could pause the video and read through them. And there are several different types of paths that motion can take. They can take a straight line, and we spend a lot of time talking about motion in a straight line. We also talk about motion. The two blanks here would be like in a circular motion. So we're going to spend a unit talking about circular motion and what does it mean when an object's traveling in a circle? Well, how do we calculate that in physics? And then there's motion that travels in an arc, and that's kind of like if you have an object that goes up and comes down. Okay, and then there's back and forth vibration, like a swing. A person swinging back and forth, or a grandfather clock where it's going back and forth. Okay, those kinds of motions. Now, straight line, okay, is really relatable to describing motion at a place and time. Okay, and that's the blanks here. You must be able to answer the questions of where an object is and in describing its motion. All right, now this is a great diagram. Okay, if you take a look at this guy, you'll see that there's a person, and there's an arrow here that represents that the person is moving. There's also something something else here that's very important, and that is the background. Okay, when you're describing motion, okay, and like this, it's called a motion diagram. And motion diagrams are very useful to us in the sense that we get an idea of how the person's moving. Notice that the feet are changing each time around. Notice that the person is changing with respect to, let's say, this tree and this lamp post, okay, and the little lake in the background. So we get an idea that the person is moving. The whole purpose of a motion diagram is to make sure that the person is indeed moving relative to their background. And I'm going to say that with emphasis. The point of a motion diagram is so that we can describe a person's motion with respect to their surroundings. Okay, now a particle model, which we'll talk about in a little bit more detail in a little bit. Particle model would be like taking the person and instead of drawing their, their legs and their arms and their torso, you would just draw them as a particle. This allows us to narrow our focus. It also gives us points at which we can easily measure from like point A to point B. Because if you tried to measure this person in this diagram, let's say from his foot here, okay, and you were to measure over the distance that the person moved, notice that the foot has moved. So it's not the best representation of the motion of the person as a whole. So, moving on. Particle models. Here's just some examples of what a particle model is. It's basically taking a motion diagram, so a picture of a person moving with respect to their background, and it's taking that object and it's turning it into a particle. Okay, and so it's a simplified version of a motion diagram. Basically the idea down here at the bottom, simplified version of a motion diagram. Here's a couple questions you can pause, see if you can answer it. Here is the answer. Okay. The statement that best describes the motion diagram is it's a series of images showing the positions of a moving object at equal time intervals. The purpose of a motion diagram, take a moment, pause. Okay, the purpose of a motion diagram is to check whether an object's in motion. Okay, all right. The explanation behind this is, in a motion diagram or particle model, we relate the motion of the object with the background. So, and that could even be surroundings. So let's say I look at a car traveling down the road. If you look out just out the road, outside at a car, and you couldn't see its background, you couldn't see the road, you just saw a car, and let's say you were both traveling at the same speed, it would look like the car wasn't moving. However, when you see the car, and you see the ground, and you see the background and the buildings going by, you realize that not only is the car moving, but you're moving at the same rate as the car. So the background is important. It gives us perspective. Okay? Now, when we draw these motion diagrams, these particle models, we have to have a coordinate system. The coordinate system is crucial to setting up the appropriate problems. So, for instance, here's some of the essential questions that I hope that we'll answer. Okay? All right. When we talk about a dimension, that's the blank here. It's an extension in a given direction. One dimension would be along a straight line. So if we're looking at a person moving from left to right. 3 dimensions would be a person, let's say, moving left, upwards, and away from us. So when we talk about dimensions, it's an extension in a given direction. Is it going away? Is it going up? Is it going left to right? Is it coming towards us? Is it going down? Okay, those kinds of things. Now, some new vocabulary we would discuss in this unit would be the coordinate system and defining what does that actually represent and mean. Then there's the origin, position, distance, magnitude, vector, scalar, time interval, displacement, and resultant. And all of these things are very important for us in our study. So, first of all, a coordinate system, and that's the blank here. A coordinate system tells you, and this is very important, there are 2 things a coordinate system does. First of all, it tells you the location. Okay, I want to zoom out here. It tells you the location of the 0 point, and it also tells you the direction in which the values of the variable increase. Okay? So when we're talking about a coordinate system, we're talking about 2 things. The 0 point, where does the object start? And then which direction is the positive motion? In which direction is that person's, the variable, whether it be how far the person is from where you are or how fast they're going. In which direction does that increase? So the 0 point has a very special term, and it's called the origin. Okay, so this blank right here would be called the origin, and it's one of the vocab words on the previous slide. The origin is where does the person start? And not necessarily even where they start, but where they started. So let's say you could describe it as I started at the origin, and I moved 10 meters. Okay, that's fine. Or you could say I started 5 meters from the origin and moved 10 meters. both of those things are in reference to this 0 point. And it could be any point. You could be in a classroom, and you could be moving across the classroom. And as you move across the classroom, you could say, well, the origin is that wall over there. Now, you could start at the wall. You could start wherever, but you've set your 0 point to be the wall, and this is very important. In the example below, we see that there is a origin. It's right here, so where this runner starts, and they're moving from left to right. We see the direction of positive increase is from left to right. We see that the person is moving with respect to their background because as the images in the background stay still, the person is showing progressive movement. We know this is a motion diagram because the distance between the runners is relatively the same, but that's not even the most important thing, as it's the time intervals between them are the same. Okay, so we see a lot of different things going on here. Okay, the motion of this person is in one dimension, thus your measuring tape should lie along that straight line, and we see that here. Okay, now, there are three terms that we're going to have to define in this particular unit. The first is position, the second is distance, the third is displacement. And though they all sound like they're measuring very much the same kind of thing, they all have units of meters, they all are talking about some kind of where the object is, okay, they each represent a little bit of a different idea. For instance, distance is how far an object goes total. So let's say you go to the store, go to the movies, go home. Your distance traveled would be how far it was to the movies plus how far it was to the store plus how far it was to the movies plus how far it was home. The whole path all together. Your position is always in reference to your origin. So looking at this diagram, this comes into play because both of these arrows are position vectors. They're position arrows. They're starting at the origin, okay, so they're with respect to the origin, and they're drawn to some stopping point. This top one to the 10-meter mark, this bottom one to the 30-meter mark. The two arrows locate the runner's position, which is the blank, at two different times. So the runner was, okay, here at this particular time, the position of 10 meters, and then the runner was here at a position of 30 meters. Okay, so that's what we're talking about. When we say position, we draw these arrows, and we always draw them from the origin. Okay, now the length of how far an object is from the origin, okay, the length of how far an object is from the origin indicates its displacement from the origin. So let's say the origin was here. Oh, excuse me, that is the wrong statement. It's its distance. The length of how far an object is, the length, just the length, is its distance. So we would say that where the arrow is pointing, this would be a distance of 5 meters from the origin. Okay, now we don't have to necessarily define everything from the origin. We could define it, let's say, from this tree. So in this problem, we could say, okay, this point here is 5 meters from the origin, or it could be 9 meters from this tree. All right, so we can, as long as everything stays relative into scale, we can describe this in several different ways. All right, now this is one of those main key ideas that you want to focus in on, especially for your test. The idea of vectors and scalars. Basically, when we're talking vectors and scalars, we're talking about this idea that vectors have two properties. We call the first property magnitude and the second property direction. Whereas scalars have just this idea of magnitude, not direction. Give you an example of how these differ. A vector might be the person is running northeast at 5 miles an hour. Well, we know that the magnitude is 5 miles an hour. The direction would be northeast. However, if I just said, hey, that person's going 5 miles an hour, I have no idea how far they're going. I have no idea in what direction. However, I do still have this magnitude, 5 miles an hour, even though I don't have direction. So vectors and scalars. Vectors, the big difference is it takes into consideration direction. North, south, east, west, left, right, up, down, okay, and everything in between. Scalars take into consideration just the value of a particular number. Okay? Now, in our writings, all boldface or any variable that has an arrow above it will be considered a vector, whereas normal letters, not boldfaced, with no arrow, will be considered scalars. Okay, and you can see that there. All right, a couple things here which are really crucial for us to look at. First of all, you have stopwatches. Okay, so we know time. And notice that they're using this thing TI and TF. Okay? Okay, there's also this distance that the person runs here. The difference between the initial and final times is called the time interval. Okay? And we would represent this as the following. When you say difference, you're talking subtraction. We're taking the time where the person ended up and we're subtracting the time where they started, and we're going to say that that's the difference or the change in. Now, this Greek letter delta, which looks like a really fancy triangle, is our symbol for change. So we would actually write this whole equation as being delta t equals tf minus ti. And you might be wondering, why would we write TF minus TI? Why not the other way around? And the answer is that because time is always moving forward, TF will always be larger. And you want TF to be larger because when you do your subtraction, then you will always end up with a positive answer. You want a positive answer because time can't be negative. A negative time would indicate that you've gone back in time. And though that's awesome and cool and neat to all extents, it's not possible. At least not possible yet, according to man's current knowledge of the scientific world. So, this being the case, we would say that this is called a time interval. It's the time that has occurred over from our starting time, TI, our initial, to our final time, TF. Okay, and you can see it here nice and neatly defined mathematically. The I and the F, and I've already kind of alluded to it, stand for initial and final times. Okay, so initial and final times. And the time interval is a scalar quantity because the time is just given to us in minutes, seconds. There is no direction. Time is always moving forward, so it is a scalar quantity. All right, this is a great diagram. There's a lot going on here. First of all, we have two position vectors, okay? The origin is here. And we see that we have not one arrow, but two that are drawn with respect to the origin. Those are called position vectors, okay? Because and I did not want to zoom in like that. Go ahead and zoom out there. Okay, they're called position vectors because they both are starting with respect to the origin. Now, this here is delta x, and like in our previous, okay, this delta symbol represents a change in. X, just so you know, is representative of our position. And as we move throughout our units, X and D become kind of one and the same. They mean the same thing. D will not necessarily mean distance. It actually means position because we're always measuring position of an object from its origin. Notice that this vector goes this far. This vector goes this far, okay, so from left to right. And what ends up happening there we go. All right, so no, we're zooming out, okay? So, here we go. All right, so when we look at this, we have our final position minus our initial position. That's a change in position, and that's where we see this delta x come into play. So we're going to go ahead and move on here, and we're going to see that these arrows not only have magnitude, they also have direction, so they're vectors. You can see a close-up here of these particular values we've been talking about. The delta x, which means change in position, our final position here, our initial position here, and this change in position will actually have a special value, which we're about to discuss. Okay, this special value is what we call, well, let's talk through this first. Xi represents the position of the tree, Xf represents the position of the lamppost, and delta x represents the change in position, okay, or the displacement from the lamppost. The displacement is defined mathematically as this. Notice how it's very similar to the time interval. You have your delta, you have your variable f minus your variable I. This format will not go away. It comes back again and again and again. All right. There's also vector addition and subtraction, and this should be something you're familiar with from your math class. Just so you know, when you're adding vectors together, there's a special term for this. We call vector addition and subtraction what you end up with, the resultant. And we're going to really explore this idea of vectors more as we progress throughout the semester. Basically, if you have two vectors headed in the same direction, okay, then you can add them. If you have two vectors headed in opposite directions and they represent the same type of quantity, you can subtract them. So, and then whatever you end up with is called your resultant. We see a resultant here, we see a resultant here, we see a resultant here. Okay, you could really take a look at this diagram, and if you have any questions, email me. Okay, and that basically ends. You can go ahead and read through some of that by pausing the video. That basically ends this particular lecture on Unit 1, Unit 2, our introduction to velocity. Really looking at some of those key concepts of time interval, vectors, scalars, coordinate systems, and whatnot. If you have any questions, feel free to email me. Otherwise, have a great day.